All right, let's do one more example with linear dependence and independence. This is example 1.4.5. I'm going to assume that I have a set of three vectors, u, v, and w, which is linearly independent in a vector space V. So I don't know if these are function, matrices, or some crazy math object. We don't know any of this, but what we do know is that they're linearly independent. So the only way to write a linear combination that gives you 0 using them is to take 0u plus 0v plus 0w. That's it. All right, so I want to determine whether this new set built from S is linearly dependent or independent. If possible, give a dependence relation. All right, so what we're given is that if I manage to write, I'm sorry, let me use all A's, a 2v plus a 3w, if this gives you 0, then that means that all the constants in front of our elements need to be 0. All right, and then we want to consider the same type of problem of writing 0 as a linear combination, but with these new vectors. So let's use different letters. So b1 times the first plus b2 times the second. Oh, sorry, plus 6w plus b3 times the third. I claim that I want this to be equal to 0. And now I want to know, do I have different ways of doing this? Do I have different values for the bi's, or do I need to take them all to be 0? All right, so I want to go from this linear combination of more complicated vectors to one that looks like this. So I'm going to distribute the constants in, and then I'm going to put all the u's together, all the v's together, and all the w's together, and I'm going to get something like that, and I'll be able to use this implication and get that whatever those coefficients in front of u, v, and w are, that combination needs to be 0. All right, so I'm getting 2b1u plus b1v. I'm getting b2v minus b2u plus 6b2w plus b3u minus b3w equals 0v. All right, I'm going to put all the u's together. I have u here, here, and here. So I'm going to get 2b1 minus b2 plus b3 times u. I'm going to take all the v's. I have this one, and that's it. So I have b1 plus b2v. And then the w's, I have 6b2 minus b3. And I'm assuming that this gives me 0, and so by star, because my vector that I started with, these vectors are linearly independent, I know now that the coefficients, which is all of this, needs to be 0, this needs to be 0, this needs to be 0. Notice that it doesn't solve the question for S1 because it's not this sum that I need to be 0. I need B1, B2, B3 to be 0, so we still need to do some work. So I get that the coefficient in the expanded version need to be 0 because I was told that u, v, and w formed a linearly independent set. All right, so I get that 2b1 minus b2 plus b3 is 0, b1 plus b2 equals 0, and 6b2 minus b3 equals 0. I'm going to put that in a matrix. Notice that these are actually numbers, right? b1, b2, b3 are real numbers. So now I'm working in a world that we know well. I'm looking in the world of real numbers. All right, so this is the system I need to solve. I've done it for us. I got 1, 0, 0, 0, 1, 0, 0, 0, 1. And so I get that I need to take B1 equals 0. I need to take B2 equals 0. I need to take B3 equals 0. And so S1, the new set, is also linearly independent. All right, that was it for this video.